are doing lesson 7.4, sample means. So we typically use sample proportions when we are interested in categorical variables. We ask questions like, what proportion of M&Ms are red? What proportion of Rockridge students watch whatever the latest show is? What if we want to know the average height of a grade 12 student, the mean income in a neighborhood, or the expected blood pressure reading of a 50-year-old male? These are all quantitative variables, and we are interested in their mean. In this section, we will explore the sampling distribution of the sample mean. So let's consider the situation where we have a bag of 1,000 pennies. The applet that's listed here did not work for me. You can give it a try, but we're right now going to have a look at a different website, and it is called Online Statbook.com stat_sim sampling dist _dist. So you can give that a try on your own, but let's have a look at it together. And so here you can see we've got the parent population at the top, and in a minute we can change what that looks like. And we're going to, you can animate it and have things drop down, but we're just going to jump in. We're going to start with an N of 5, and we're going to do 10,000 samples instead of 100. And that's what the mean looks like, and we can see that the mean here, we get different numbers obviously than what I'm going to put down, but we can have a look at that, and we can see that the mean pretty much fits the normal. So we can then go ahead and change our N and look at 10. And sorry, I've forgotten if we did 100 or 10,000. Anyway, once again, we get a normal. And if I change to 25, we will see again a nice normal. Now I want you to pay attention. Let's sit back again. Pay attention to the spread. Oops, sorry, just a minute. So pay attention to the spread. When we had n equals 5, we had a fairly wide spread, and n equals 25, we have a narrow spread. So our standard deviation gets smaller as our sample size gets larger. You'll also notice that that it does tend to follow a normal distribution, so it's unimodal and symmetrical, and it gets taller and thinner as n increases. So what we're going to do now is change things up a bit. I'm going to make my sampling distribution skewed. Okay, what happens to our mean? So you can see here where the mean is roughly, and we'll stick with 25 is fine. And our mean pretty much looks, we can add some more repetitions, but I mean pretty much is the sampling mean still is fairly normal. Okay, I can even do funny things like cut out a section and have something that have a parent population that is not normal, is not unimodal, and let's try that one. So once again, we'll just stick with 25, we'll go 100,000 again, and lo and behold, our distribution of means stays normal. So that's a really neat thing, and you'll also notice that we have a nice lineup with the mean of our parent population. So we're going to zip back to our notes, and we'll just go through a random variable x. We're going to use some data from a previous sample using the app that was originally listed here. And the standard deviation for each of these, they were all symmetrical, as we also found. and unimodal. The mean always stayed the same, roughly. However, the standard deviation, as we can see, gets smaller as we get a bigger number of samples. Now, we're going to calculate the standard deviation of our population divided by the square root of n. And so, in other words, it's, in this case, 9.61 was our given data divided by the square root of n. So for each of these, you can see that the numbers are roughly the same as in our simulation. Okay? So what did we notice? If you recall, we've already mentioned the standard deviation of the sampling distribution is very close to the standard deviation of the population over the square root of n. Okay, and we notice that all sampling distributions were unimodal and symmetrical, and that the distributions got taller and thinner. Taller and thinner as n increases. So as n went up. We can see this in the standard deviation of our sampling distribution. So listed above as well in the standard deviation of our sampling distribution. Okay, so going down a bit, the sampling distribution of the sample mean is what we're looking at now. So suppose that x bar is the mean of an SRS of size n drawn from a large population with mean mu and standard deviation sigma. Then the mean of the standard deviation of x bar is equal to the mean of the population. Therefore, we can say that the sample mean x bar is an unbiased estimator of the population mean. Remember, unbiased means that it is equal to. So we can use a sample mean to estimate what the population mean is, because of course we don't always know what the population mean is. We can't sample every single, we can't survey every subject in our population. The standard deviation of the sample distribution of x bar, so sigma x bar, equals sigma over the square root of n. And so this is the population sample standard deviation divided by the square root of the sample size. Okay. Now we can use this as long as our independence condition, remember, is that n is less than or equal to 1/10 of the population size. As long as our independence condition is satisfied, And this means that we get less spread. We get less spread in our sampling distribution if n is larger. Because when you divide by a larger number, things get small. Now, remember when we changed, in our example, we changed the shape of the population? So these properties are true no matter what the shape of the original distribution. Okay, we're going to pause here. Now, we're going to have a quick look at why the standard deviation of a sampling distribution is divided by the square root of n. So first we'll look at the mean. Sorry, just a second. We'll look at the mean of the standard. The mean of the sample means. So if x bar, as we know, that is going to be equal to the mean. For each sample, we would expect its average to be the mean. So if I take the average of a whole bunch of samples means, when we do average, remember, we are going to sum up the means and then divide by the number of things we have added up. Now, if the means are all the same, then the sum of them is going to be equal to n times our population mean, and then we're dividing by n, so we get mu, which is what we found in our example so far. For the standard deviation, what we can think about is that once again, we have to divide by the number of samples again. Just like we would for finding the mean, for finding an average. But when we add variables, random variables, to find the standard deviation, we actually have to add variance. So the standard deviation of our mean, of the means for our sampling distribution, is going to be the square root of the sum of the variances, and of course the variance for each sample is going to be the same as our population variance, and then we divide all of that by n. So in this case, once again, if they're all the same, we're going to have n of them, and then divide by n. If we put that into the brackets, we would have n sigma squared over n squared, and then of course one of those n's cancels out. We get the standard deviation of our population divided by the square root of our sample size. All right.